So now we're going to look at the work energy theorem and its relationship to kinetic energy. First of all, kinetic energy, which is the energy of objects in motion, is equal to 1/2 mv squared. And remember, this is always going to be positive because you can't have negative mass and you can have negative velocity, but when you square it, it's going to become positive regardless. So that is the formula for kinetic energy. Now, the work energy theorem says that when a net external force does work on an object, the kinetic energy of the object changes according to the net work. Meaning, the net work is equal to the change of kinetic energy. Now, change of kinetic energy, the change of kinetic energy is the same thing as saying that the net work is equal to the final kinetic energy minus the initial kinetic energy. And when we combine it with our equation that says net work is equal to net force times the displacement, or the dot product of the net force and the displacement is equal to net work, we can combine them and get a new equation that says that the kinetic energy final minus the kinetic energy initial is equal to the net force magnitude times the displacement times cosine theta. And that could help us solve some more complicated problems like the one we're going to do next. So let's use this equation. So here we have an example problem where we have the mass of the space probe. They tell us that the mass of the space probe is 474 kilograms. They also tell us that the initial velocity is 275 meters per second. And then they further tell us that the net force experienced by this satellite is 2.42 times 10 to the 9th. Tell us that the net force is 56 millinewtons. Now, millinewtons just means that it's 56 times 10 to the negative third newtons is the net force. And then they also tell us that the displacement is equal to 2.42 times 10 to the 9th meters. And they want to find out what the final velocity is what the question is asking. Now, anytime we see final velocity, initial velocity, and displacement, we should kind of already jump to our kinematic equations. Now, we could use kinematics to solve this. The kinematic equation we would use to solve this would still need one more variable. But we can use that by combining the net force and the mass to find the acceleration. Once we know the acceleration, the v initial, the displacement, we can find the v final by using the v final squared equals v initial squared plus 2ax. Now, we're not going to use that equation because we're talking about energy. So instead of using that equation, we're going to use the net work equals change of kinetic energy equation combined with the net work equals force times displacement cosine theta. And we're going to find out that we get the same answer. When we combine these equations, we get that the kinetic energy final minus the kinetic energy initial is equal to the dot product of the magnitude of the F times displacement times cosine of theta, which is the equation below. And when we plug in our values, we can solve for it. We know that cosine, since they're pointing in the same, the force and the displacement, or they told us is pointing in the same direction, they don't have to say it. Net force and the displacement are parallel to each other, so the angle that they make is 0 degrees. So this is going to become 1. And then as we solve for everything, we can solve that our final velocity is 805 meters per second. As extra practice, you can try to calculate how long does it take to reach that speed. You can use that using the final velocity, the displacement, the initial velocity, and the possible acceleration you calculated, and you can figure out what the actual time is. Well, probably the best equation to use was the displacement is equal to v final minus v initial over 2t. Now the displacement, you just calculated the v final, they told you your v initial, and then you can calculate t. So you really need to know the acceleration. There's a big relationship, if you didn't notice from the last slide, between the kinematic equation Vx squared equals V initial squared plus 2ax, and the work energy theorem. Basically, imagine we multiply everything by mass. We take this whole equation and we multiply it times the mass. Or before we even do that, we just move over the V initial squared. So we end up with V final squared minus V initial squared equals 2ax. And then let's divide everything by 2, meaning we have 1/2 V final squared minus 1/2 V initial squared equals ax. Because we took everything and we multiplied it by 1/2. Now, if we multiply everything now, as long as we do everything to both sides, this equation is still true. By the m, we end up with 1/2 V final mass, or better yet, 1/2 m V final squared minus 1/2 m V initial squared is equal to m a x. It's the same equation. This work energy theorem is where our fifth kinematic equation came from, just a simplified version. This is actually better because it accounts for the mass, which could change, which could come later, and especially if we do some integration. But that's where our equation comes from this work energy theorem. Where would we be without our fifth kinematic equation? All right, some quick concept question. A satellite is moving about the Earth in a circular orbit and an elliptical orbit. For these two orbits, determine whether the kinetic energy of the satellite changes during the motion. Let's quickly touch up the problem. So you have the following question. It says you have a satellite moving in a circular path and a satellite moving in an elliptical. And they want to know in which of those the kinetic energy of the satellite change. Well, if we look at part A, this vector not is pointing at the same direction as the velocity. The velocity is always perpendicular to the center of it, which is also your motion. So if you notice here, the velocity, or more importantly, the displacement, and the force are always perpendicular to each other. Which means when we try to find the net work being done, we're going to end up with the force of gravity, which is the only force acting on it, which is the net force, times the displacement, however far it goes, times cosine of 90. So we're going to, the net work is 0, which means the change in kinetic energy is also going to be 0, which means as an object moves around a circular path, its kinetic energy is constant. This is not the same case for the elliptical orbit. As you can see, as the elliptical orbit goes, part of it being an ellipse is that the angle is not 90 degrees, meaning the force of gravity is doing some kind of work. First, it's doing, in this case, negative work here. And then in this case, the angle being made is doing positive work. So as it moves through the circle, the amount of the net work actually exists. It's not going to be 0. That depends on the angle, which means that there is a change in kinetic energy, which means the kinetic energy is not constant. Which is really important when we start talking about Kepler's law, but that comes much later. Alright, some concept questions. A sailboat is moving at a constant velocity. Is work being done by a net external force acting on the boat? The answer is no. Because it is moving at a constant velocity, that means the net work, which is the net force, times d cosine theta, well, the net force is 0. It's moving at a constant velocity, which means the forces are canceling out, so that there's no net work being done. For part number 6, a ball has a speed of 15 meters per second. Only one external force acts on the ball. After this force acts on the speed of the ball is 7 meters per second. Has the force done positive work, 0, or negative work? So the ball went from 15 meters per second to 7 meters per second. So its velocity, its change in velocity, was negative. Which means the change in kinetic energy, which is equal to 1/2 the mass times v final, we can say change in velocity, is also going to be negative. Now, keep in mind, kinetic energy of an object will always be positive. But that doesn't mean the change in kinetic energy can't be negative. You can have a negative change in kinetic energy. Anytime an object slows down, it's getting it has less kinetic energy, which means it lost kinetic energy, which means its change is negative. So it is possible to have a negative change in kinetic energy, but you can't have a negative kinetic energy. But back to this, since the net work is equal to the change in kinetic energy, that means the net work must also be negative. So, the question, has the force done positive, 0, or negative work on the ball? The force, since there's only one force, and that force is equal to the net force, must be doing negative work. A rocket is at rest on the launch pad. When the rocket is launched, its kinetic energy increases. Its kinetic energy increases, which means that its velocity is increasing, which means its change in velocity is positive. Consider the following forces acting on the rocket during the launch and decide whether the following statement is true or false. So if we think about a rocket, if we look at all the forces, there's force of gravity acting down on the rocket. There's the engine or the thrust pushing down. And if we want to get really accurate, there's probably some kind of friction or resistance, whatever, air resistance, pushing it back, trying to slow it down. So the question is to decide whether the following statement is true or false. The amount by which the kinetic energy of the rocket increasing during the launch is equal to the work done by the force generated by the rockets of the engine. Increases in launch pad is equal to the work done by the force generated by the rockets. The answer is false. For several reasons. Oops, ended up going backwards. One of the reasons is that there's too many forces. The faster you go, the wind resistance, usually the force of friction caused by the wind is equal to some kind of constant squared, where x is your velocity. So the faster you go, the more wind resistance, but that's not the only reason. Force of gravity is constantly changing. The higher you go above the earth, the less your gravity becomes, so your gravity is changing. So it's not just simply your thrust, because the kinetic energy doesn't just affect your thrust, the kinetic energy affects your net force. So the kinetic energy it's equal, it's proportional, the change in kinetic energy is proportional to the change in your net force. And we can talk more about this in class, especially since we have this equation that we can discuss. Part 8 says a net external force acts on a particle that is moving along a straight line. This net force is not 0. Which one of the following statements is correct? So the net force is not 0. But we don't know if the net force is moving in the same direction or opposite direction of the displacement. So one possible situation is that the force is this way and then the displacement is this way. That's the net force we're talking about. Or the net force could be pointing this way and it's moving in the opposite direction of the displacement. We don't know which one's happening, we just know that the object is moving and the net force is not 0. So the velocity but not the kinetic energy of the particle is changing. Let's see, part A. The velocity, but not the kinetic energy of the particle, is changing. The velocity would change because net force means you have an acceleration, but because you have a net force, that also means you're going to have some kind of change in kinetic energy. So the kinetic energy will change. The kinetic energy, but not the velocity of the particle, is changing. The velocity is changing because you have acceleration. Both the velocity and the kinetic energy of the particle are changing, so your best solution is C.